So I dropped this little nugget on class today. I found this problem online. I assume that the teacher that wrote it, his name is Corpy. But anyway, a ladder with Corpy on the rungs is to reach over a fence 8 feet high to a wall 1 foot behind the fence. This will allow Corpy to access a window where a dastardly student awaits to drop a calculus book on his head. What is the length of the shortest ladder that can be used? Assume a black cat will be beneath the ladder. Okay, so there's a lot going on here, but a few pieces of important information. First of all, our optimization has to do with this ladder. We want to find the shortest ladder. The black cat thing doesn't really apply here. And really the only information we're given is that there's a fence that's 8 feet high that we have to go over. So let me see if I can draw a picture of this thing. I've got a wall, apparently, right here. We'll draw the wall in. Pretend that's a wall. I'll color that in. And, you know, the window's up here somewhere probably, right? Okay. And then I've got a fence. Oh, what color's our fence? Let's make our fence yellow. I got a fence here that's 8 feet tall. Let's see if I can make that look like a fence. Okay, that's 8 feet tall. It's 1 foot away from the wall. Okay, and then we're going to have a ladder that we have to go over the fence, and we're trying to get to the top of this thing. So the ladder is going to go something like this. Pretend this green thing is my ladder. Let's put some rungs on it so it actually looks like a ladder. Okay, so there's the ladder. And let's put a little bit of a ground down here. Okay, so that's our situation. I'm going to add one more piece of information in here, which is I'm going to draw a parallel line to the ground right there. So this is also 1 foot. But that helps me set something up on this problem here. This distance is 8 feet, just like the yellow distance. What I don't know is this distance here. And I'm going to call that W because it's along the wall. As I mentioned down here on the bottom, this distance here is 1. But I don't know this distance, so I'm going to call that X. So when I do that, what I find out is that the entire base of the big triangle is X plus 1. And the entire height of the wall up to the window is W plus 8. And remember, we're trying to optimize the length of the ladder. So I'll call that L. Okay, so first of all, we do have a constraint here. And you've got to really want to see it, though. You've got to remember your similar triangles from geometry class. So I have a triangle up here. Let's try and circle this. I guess I'll circle it in yellow. This triangle up here, this little one, that triangle is similar to the big triangle. And so I can set up a proportion because you know that the corresponding sides are proportional. The big triangle, that big triangle has a proportion or a ratio of the tall side, W plus 8, over the bottom side, X plus 1. And then the little triangle has a tall side of W and a short side of 1. And so I've got this proportion, right? I can cross multiply and I get W times X plus 1 equals W plus 8 times 1, which is just W plus 8. And then I can divide both sides by W. Right, I divide both sides by W and I get X plus 1 equals 1 plus 8 over W. And then if I minus 1 on both sides, I get X equals 8 over W. And that must mean that W equals 8 over X. So you can decide which way you want to write that constraint, but the bottom line is we've either solved for X or W. I'm actually going to use the I'll use this w equals 8 over x. And so that way my function will just have x's in it. Okay, so let's write that objective function for L. Our objective function, L, or if you want to call it L of x, that's fine. That's going to be, we're going to use the Pythagorean theorem, right? It's x plus 1 squared plus w plus 8 squared equals L squared. That means that L is the square root of x plus 1 squared plus w plus 8 squared. And then what I'm going to do is I'm going to replace w with 8 over x. So this is now x plus 1 squared plus 8 over x plus 8 squared. So that's my objective function. All right, and that's the thing I'm going to take the derivative of. I think I might multiply these out first. But once we get this relationship with the constraint, we're able to write that objective function. It just took a minute to think about the similar triangles to get there. So let me switch to a new slide where I can clean this up and then take the derivative so that I can optimize the situation. So here we are in a new slide. We got a little room to work here. This is my objective function. What I do want to do is, I'm not going to do the derivative yet. Let's just see if we can clean this up a little so the derivative is a little easier. If I distribute this out, better known as FOIL, I'm going to get x squared plus 2x plus 1. And then over here I'm going to get 64 over x squared plus 128x, 128 over x plus 64. And we can just combine some terms here. 64 and 1 we can add together. So I'll have x squared plus 2x plus 64 over x squared plus 128 over x plus 65. And that is about as good as it's going to get. That is our objective function with everything multiplied out. To do this derivative, I have to do the chain rule. So it's going to be 1 over the 2 square root of u, 1 over 2 square root of u, and u prime will be on top, u prime over 2 square root of u. So the derivative is going to end up on top. That's going to be 2x plus 2 minus 128 over x cubed minus 128 over x squared. And then the 65 turns to a 0. And then down here it's just 2 square root of all the stuff that I had before, which is just, x squared plus 2x plus 64 over x squared plus 128 over x plus 65. Okay, so that is a nasty derivative, but the good news is, well, there's a couple things. First of all, I think we can cancel some 2's. Right? If I cancel this 2 with all these and make these 64s, that cleans it up a little bit. So let's go ahead and do that. This ends up being x plus 1 minus 64 over x cubed minus 64 over x squared. And then down here it's just the square root of our original expression, 2 plus 2x plus 64 over x squared plus 128 over x. And I'm going to squeeze this in plus 65. And it's really messy and it's hard to read, but it turns out it doesn't matter. When we set this derivative equal to 0, we're really only going to be interested in when the numerator equals 0. So to find the critical point, I'm just going to set x plus 1 minus 64 over x cubed minus 64 over x squared equal to 0. And we've had some stress lately about fractions. So remember, I've instructed you several times on how to get rid of fractions. Essentially, we just multiply the whole thing by x cubed because that's the common denominator. So I'm going to multiply both sides by x cubed. And that makes this x to the 4th plus x cubed minus 64 minus 64x. Now, since it's minus 64 and minus 64x, do you mind if I just make it minus 64x minus 64? I'm just going to commute those two terms. I can do that as long as I keep the signs in the right place. I'm just doing that so that it makes my factoring a little easier. So we took the derivative. It was a nasty fraction, right? A rational function. But when we set it equal to 0, we're only worried about when the numerator is 0. Okay? And so I'm just going to set the numerator equal to 0. To get rid of the fractions, I multiply by x cubed, and I end up with this quartic, right? X to the 4th plus x cubed minus 64x minus 64. Turns out that bad boy is easy to factor. So let me get a new slide here, and we'll just factor this thing and finish it off. Okay, so here's our equation. I'm going to factor this thing, and it's kind of set up for some easy grouping. So if I split this into two pieces right here, if I pull a GCF out of x to the 4th plus x cubed, that's x cubed times x plus 1. If I pull a minus 64, a negative 64 out of these two terms, I get negative 64 times x plus 1. Right? And the way grouping works is we have a common binomial factor of x plus 1. So I'm going to write that down here. And then I have these leftover terms, x cubed minus 64 equals 0. And then now we have the zero product property. This is going to result in x equals negative 1 when you set it equal to 0. And that is useless to us, right? We can't have x be a negative number. So we better hope that when we set x cubed minus 64 equal to 0, that we get something reasonable. And it turns out we do. We get the cube root of 64, which I'm pretty sure is 4 feet. Okay. So x is 4. And then you'll remember that w is just 8 over x. So w is going to equal 2 feet. Now, we need those measurements so we can figure out L. They want to know what is the shortest ladder. And if you'll recall our formula, it was the square root of x plus 1 squared plus w plus 8 squared. So this is going to be the square root of, let's see, x was 4, so this is 5 squared, 25, plus w is 2, 2 plus 8, that's 10, that's 100. So we're talking about the square root of 125. If you're going to reduce that, what is that? That's going to be 5 square root of 5, which is about 11.2. So we're talking about 11.2 feet. That's about the shortest that our ladder can be in order for us to reach the window. And yes, that was a stinker of a problem, but there's nothing in here that a geometry and algebra student, along with a calculus student that studied algebra and geometry couldn't handle. But you got to remember a lot of the stuff that you had several years ago to do it. Okay, let me show you one other way that we can solve an optimization problem once we have our objective function. We can always just graph it and look for where the minimum is. And what we're hoping is that we see x equals 4 and y equals 11.2. Let me show you what happened when I graphed it on Desmos. So over here on the left, I did enter our function in, as you can see. I'll just circle it here. It has to be a function of x. So instead of x plus 1 squared and w plus 8 squared, I did 8 over x plus 8 squared. When you graph that thing, over here at x equals 4, you can see that my minimum point there is 11.18, which I called 11.2. So we did locate our extreme value. Our other critical point was over here at negative 1. And as we said, that doesn't help us, right? We actually get a value of 0 for the ladder there when we plug in negative 1. We do not want a negative measurement for x. Remember, x was part of the base of our triangle. So, and if x were negative 1 plus 1, that whole base would just be 0, and that's no good. Okay, so I really like this problem. It was a challenge for sure, but it wasn't so hard that we couldn't figure it out once you start patiently labeling that picture with the appropriate measurements that you know. Okay, that's it for me. If you have any questions, you know where to find me. In the meantime, take care.